Welcome to the Journey Chez Chem. Well, today's warm-up is quite long, so I suggest you get working on it as quickly as possible, and we'll discuss it in a moment. In number 1, we are determining the freezing point and the boiling point of a solution. Well, this solution contains 25.0 grams of calcium phosphate, and we must always get our formula written correctly. And calcium has a +2 charge and phosphate is -3, so the common multiple is 6. Therefore, I need 3 calciums and 2 phosphates. Well, I need to get the AMU of the calcium phosphate, or the formula mass, so I'm going to write out that I have 3 calciums and each calcium has a mass of 40.1. There are 2 phosphorus with a mass of 31.0 each, and 8 oxygens. And you know that I write these out again because that's where many mistakes are made. And the total formula weight is 310.3 grams per mole. So I change my grams to moles, and I get 0.08056 moles of the calcium phosphate. Now, this initial 0 is not significant, and it is very important that I follow this process correctly because the assessment will have multiple choice questions for 60% of it, and you'll need to make sure that you use these numbers as we do consistently. And so this is 4 significant places after the decimal, and we cut it off, we truncate. Now I have to divide the moles by the kilograms of solvent. Well, I'm given 239 milliliters of water, and 1 milliliter is 1 gram. And then 1 kilogram is 1,000 grams. And therefore the denominator is 0.239 kilograms. Now, when I divide this number, I get a molality, which I'm going to use in both problems, of 0.3370 molal of the calcium phosphate. And now, in order to get the freezing point and the boiling point of the solution, first I'm going to do the change in the temperature of the freezing point is equal to the molality times the freezing point depression constant times the number of particles. Well, I know that calcium phosphate is going to give me 5 particles. I get 3 calcium ions, and they must be ions because without the charge, they're not ions. And I have 2 phosphates. So we have a total of 5 particles. 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 That's right. You just have to spell it and look at it sometimes to get it right. Therefore, I am going to use my molality of 0.3370 molal, and the freezing point depression constant for water, which is my solvent, is 1.86 degrees Celsius per molal, and then there are 5 particles. And when I do this math, I am going to get 3.1341. Now, water normally freezes at 0 degrees Celsius, and we know that freezing point goes down, and therefore 0 minus 3.1341 equals minus 3.1341. I go back to my original number to see how many significant digits in my answer, and there should be 3. Therefore, my final freezing point of this solution is 3.13 degrees Celsius. Now, the process is very similar for boiling point. The change in the temperature of the boiling point is equal to the molality times the boiling point elevation constant for that solvent, and therefore I have 0.3370 molal. My constant for water is 0.512 degrees Celsius per molal, and then there are 5 particles. Now, when I multiply this out, the change is 0.8627. Notice before I get my final answer, I am using the number 4 places past the decimal and I cut it off. Well, water normally boils at 100 degrees Celsius and boiling point goes up, boiling point elevation. So I add the 0.8627. Now we have a very special rule for boiling point. Because these changes are so very small, we're going to go 3 places past the decimal rounded. And therefore, my final answer is 100.863 degrees Celsius for my boiling point, my new boiling point for this solution. And my freezing point was minus 3.13 degrees Celsius. The number of particles is all what colligative properties are all about. Therefore, we must take them into consideration. Well, I'll be right back to talk about number 2. Number 2 is very similar to the types of understanding of materials that we're going to need for the assessment. And 40% of the assessment is terms and fill in the blank. Now, it is important to be able to figure out the number of particles. Well, sodium sulfate, again, we're reviewing our nomenclature, is all of this sodium sulfate is a salt. And so when I put it in water, I get 2 sodium ions and 1 sulfate ion. Sulfate, as you recall, stays together as a unit because it's a polyatomic ion and they're sharing electrons. So we get a total of 3 particles here. Now in zinc phosphate, we get 3 zinc ions and 2 phosphate ions. Again, the polyatomic ion stays together as a unit and we get a total of 5 particles. Now, glucose is a non-electrolyte, and that's why it was very important for us to understand weak, strong, and non-electrolytes because we were coming up to this point. Well, glucose being a non-electrolyte is not going to dissociate into particles, and oftentimes students will want to add up these numbers and think that they just go into their atoms, and they don't do that. It stays together. When you put sugar into water, it stays as sugar. It does not dissociate into particles. So we only have 1 particle here for glucose. And then we have perchloric acid. Now you'll notice that I picked a strong acid because they have 100% dissociation. And we get hydrogen and perchlorate ions, and therefore we get 2 particles. And then we have magnesium hydroxide, and we get 1 magnesium and 2 hydroxides, which is a total of 3 particles. And that is in general what we get, and of course it is dependent upon the concentration, and we're just looking in general if we can understand how to separate them into their particles. And we'll get to more specifics and how they relate to the colligative properties in part B. And I'll be right back. In number 2B, we are actually applying this to colligative properties. And the very first thing I must do is write out the formulas. And you'll notice that all of them have the same concentration. So if we were to have different concentrations, we would have to figure out the actual amount of the ions. But because they're all the same concentration, mostly I just want to see if you understand the direction in which they go. Well, the first thing I do when I'm answering any of these types of questions is I write that freezing point goes down the more particles that I have. And vapor pressure also goes down the more particles that I have. And boiling point goes up. Then I look at the specific questions. Well, the first question about these compounds, and I see that in the first one I have 3 particles. The second one I have 3 particles, then 5 particles and 1 particle. And then I look and I'm asked for the lowest freezing point. And I see that freezing point goes down the more particles I have. Therefore, the one with the lowest freezing point will be the one with the most particles, the cadmium phosphate. Then I'm asked which one has the highest vapor pressure. Well, vapor pressure also goes down the more particles I have. So the one with the highest vapor pressure will be the one with the least number of particles, and that would be glucose. And then I have the lowest boiling point, and I see that boiling point goes up the more particles I have. Therefore, the one with the lowest boiling point would be the one with the least number of particles, and that would be glucose. And finally, the highest boiling point would be the one with the most particles, and that would be my cadmium phosphate. Very important here to understand what's going on here, because the order of which these are written on is not always the same, and therefore we have to pay attention to what we're actually looking for. And oftentimes these will be either the least number of particles or the most number of particles, depending upon the question. It's very difficult to get these others in the question, and I might ask which one has 4 particles. That way I could get to the actual specific compound that we're talking about. And that's how you do number 2. And we're going to talk about vapor pressure lowering, and I'll be right back. Now we are discussing vapor pressure lowering. Now, as we add particles to a solution, there's an interaction inside that solution between the solute and the solvent, and they're so busy with each other, it's more difficult for the vapor to get out. And they're busy. It's just like if you have a classroom full of boys and girls, there's so much interaction going on there, it takes a little bit longer to teach those children. However, if you had all boys or all girls, usually there's not that social interaction, and so you can get more teaching done. That's a little bit of an analogy. So in all of these colligative properties, as we add something to that solvent, the interaction then causes these effects. And in order to do vapor pressure, the primary equation that I will use is that the change in the vapor pressure of the solvent is equal to the mole fraction of the solute times the pure vapor pressure of the solvent. A standing for the solvent and B standing for the solute. Well, because we need mole fraction, we have to get both of our quantities into moles and then add them together. Well, I change my grams of my glucose to moles, and AMU for glucose is 180 grams per 1 mole. And I get 0.4166 moles. And this is the example problem that you're given on the very first worksheet about vapor pressure lowering. And then I have 225 grams of water, which I change to moles, and I get 12.5 exactly, so I added those zeros so that I know that those 4 digits are taken care of. Then I add them together to get the total number of moles. Now, to apply it to this equation, I'm going to erase my moles and use the information. And here I have a mole fraction of the solute, which would be 0.4166 divided by the total number of moles, which is 12.9166, times the pure vapor pressure at that temperature, for water is my solvent. And it would be 3.2 kPa. Now, on the assessment, I will also ask you for this value right here. And it needs to be 4 places past the decimal, cut off, because we need to be consistent. And it does make a difference in our answers. Well, when I do this number here, I get 0.03225 times the 3.2 kPa. Now, fractions do not have units. And when I do this multiplication, I get 0.1032. Now, we have the vapor pressure is lower, and we originally had 3.2. Now, it's dropped by this amount. So to get my final vapor pressure of the solution, I'm going to take my 3.2 kPa and subtract my change, and I get a new vapor pressure of 3.0968, and I want 2 significant digits in my answer, and therefore I get 3.1 kPa is my new vapor pressure of the solution. And you'll need to be able to get the mole fraction of the solute and the solvent on this multiple choice assessment. And that's how we do vapor pressure. And when we're numbers, the vapor pressures that we're using are dependent on the solvent at the specific temperatures. But I will give you the constants and I will give you the vapor pressures that you need. So you don't need to worry about that. Primarily, you need to understand about the process. And we're going to have more practice on this so you can get really good at it and do very well on the assessment that's coming up in a little while. But we have a couple of labs to do first. So anyway, it was sure fun being here with you today, and we've done almost everything we're going to do on colligative properties. Just one more little thing that we're going to talk about, and we'll talk about that tomorrow. And I can't wait to see you then. Bye!